Welcome everyone. In this video, we are going to discuss the SCION control plane in more detail. I hope you had a chance to first look at the SCION architecture overview video to gain some intuition of how the system works. In this video, we will then look more at the technical details of how SCION finds and disseminates paths in the network. The control plane is concerned with the exploration and distribution of end-to-end communication paths. In this video, we're going to drill down into the details of the control plane. Additional details are available in our SCION book in chapters 2.1 and 7. We'll first look at path exploration, registration, and lookup. Then we will consider security and reliability aspects of beacon propagation and SCION infrastructure services such as beacon and path servers. Then we're going to look at service anycast, and finally, we'll look at the SCION control message protocol, SCMP. Let's get started. I'll first start with a reminder about SCION isolation domains, or ISDs. For improved scalability and failure isolation, the SCION control plane is organized hierarchically, where we have a global intra-ISD and local intra-ISD routing algorithm. Autonomous systems can belong to one or multiple ISDs, as you can see on this picture where ASs X and Y are both part of the orange and green ISDs. Each ISD is governed by a set of core ASs, which constitute the ISD core. The ISD core is depicted in gray in the figure, and the ASs inside the gray area are referred to as core ASs. And we envision that these core ASs are the largest ISPs, internet service providers, within the isolation domain, and they essentially organize and manage the isolation domain. Next, we're going to look at path exploration within an ISD and between different ISDs. We'll start with intra-ISD path exploration, which we also refer to as beaconing. So in this picture, you can see a single ISD with the core ASs K, L, and M. And in this beaconing process, they initiate path segment construction beacons, or we're going to just call them PCBs for short, or also sometimes refer to them as simply beacons. So these path segment construction beacons, or PCBs, traverse the ISD as a policy-constrained multipath flood. That's quite a mouthful, so let's break this down a little bit. So under policy constraint, we mean that each AS that forwards these beacon messages has a local policy that decides which type of beacon messages should be sent. And under multipath flood, we mean that the beacons flood the whole network, and in order to reach all the different ASs in the ISD. So on this picture now, you see a set of PCBs sent by core ASK sent out, and you can see the yellow paths that these PCBs trace as they traverse the different ASs in the network. ASL similarly sends out PCBs, and you can see their paths traced as these orange lines. And similarly, core ASM sends out a beacon that goes through P and S and traces that path. So essentially, each AS receives then multiple of these PCB messages that represent path segments up to a core AS. And so each PCB can then be used as what we call up path segment. As it's depicted, the paths are traversed from the bottom up towards the core ASs in order to communicate with the core AS. So essentially, the beacon will contain enough information for any AS to send the packet to one of these core ASs. So in this slide, we'll look at beaconing in a little bit more detail. So essentially, each autonomous system, each AS deploys one or multiple beacon servers that are shown here. So in the picture, you can see ASP blown up with more detail inside, and we can see there are 3 SCION border routers shown as green rectangles, and in red we show 2 beacon servers within the AS. Now, these beacon servers essentially distribute the beacon or these PCBs through the network. these PCBs are sent as SCION service Anycast packets, which I'm going to explain more in detail later in this video. So the SCION border routers that receive one of these PCB messages, they select one beacon server inside to forward this PCB to. And then internally, the beacon servers coordinate to resend the PCBs to other downstream ASs. And currently, every 5 seconds, a PCB is sent, selected, and forwarded each inter-AS link in the network. In this slide, we're going to look more at what's actually in these PCB messages. So first, the PCB contains an info field that contains the PCB creation time and also the ISD where the PCB originates in. Each AS also adds its AS name. In this case, M originates the PCB and adds its own name M. And then also hop fields that are later used for data plane forwarding. And these hop fields contain link identifiers, expiration time, and message authentication codes. Finally, also an AS signature secures each part of this PCB message. So on the slide now you see ASs M and P with small numbers which are link identifiers. So each link that connects two ASs has a unique identifier within each AS. And so you can simply see M enumerates the 3 links it has with 1, 2, and 3 as link identifiers, or we also call them interface identifiers. P similarly numbers its links from 1 through 4, and you can see that in the hop fields, these numbers are being stored. So ASM adds number 1 to its hop field to identify that this beacon message went across or interface identifier 1. ASP then, receiving this PCB, adds the following information, its own name P, and also a hop field where it stores that the PCB arrived on interface identifier 2, and in this case it's going to be sent down to S, and so the outgoing interface identifier is number 3. Also, ASP adds a peering link, and in this case it states that the peering link exits on interface identifier 4, and the PCB is continued to send on AS3. We'll see later how these peering hop fields are being used to send packets across peering links. Also, we see again a new expiration time, and the message authentication code is added by P. This is also part of each hop field. Also, P adds its own signature and sends this PCB on to ASS. So that's essentially a high-level overview of what's in a PCB. Next, we're going to look at the path server infrastructure. Similar to beacon servers, ASs have a set of path servers which help disseminate path information through the network. And in this picture, we blow up ASs M and P, and you can see that ASM has 3 path servers, ASP has 2 path servers, and these path servers offer a lookup service. So essentially, when a client looks up a given autonomous system within a given isolation domain, so we have an ISD, AS tuple, the path server offer a set of down path segments, a set of core path segments, and the local path server will also respond with a set of up path segments to the core ASs. So essentially, again, up and down is just relative. As we depict core ASs at the top of these ISDs, we call an up path a path that goes from an AS into the core, and the down path as a path that goes from a core AS down to a non-core AS. And in essence, the paths are interchangeable, so you can convert an up path into a down path, but this terminology simplifies the description, as we're going to see in the remainder of this video. A core path then represents a path amongst core ASs, and they're needed to connect up paths to down paths. All right, so these path servers, again, offer this lookup service to look up these different sets of paths. And now the core ESs have a special operation here where they operate the core path server infrastructure, which represents a consistent and replicated store of all downpath segments and core path segments that are associated with a given ISD. Also, each non-core ES runs local path servers, which serve up-path segments to the local clients and also helps resolving as well as cache responses of remote AS lookups. So let's look at this in a bit more detail. First, an AS needs to perform downpath segment registration. So in this example, we see ASS that has received 4 different paths through the beaconing process. And this AS now selects which paths it wants to announce and register as downpath segments in the AS core. It looks at each path that it has and it decides whether or not it wants to make use of these paths and register these paths at the core AS. So for instance, it takes the first path and decides, yes, it wants to maintain this path. Also the second and third path, but the fourth, one of the orange paths, it decided not to select and not to upload. All the paths that are uploaded to a core AS then are being distributed within all the core ASs, as I'm going to discuss later in this video. So also locally, up path segments are being registered at local path servers. And the process is very similar to the process we have just seen. Essentially, each path is being considered, and in this case, the AS decides to register all the paths at its local path server. And so all these paths will be made available to the local clients who are performing path lookups. Let's take a look at core beaconing for intra-ISD path exploration. In this example, we're going to look at a PCB that is initiated by core AST and that is sent on to core ASM and later to ASJ. Core AST adds the following information. Similar to PCBs inside an ISD, it again adds an info field which contains a timestamp and an ISD identifier. So the ISD in this case is simply the orange ISD. And it sends on this PCB across the top link, which has the link identifier number 7 onto ASM. So it also adds a hop field, which will later be used for the forwarding to encode the forwarding information in data packets. And in this case, the hop field encodes the interface identifier 7, as well as an expiration time and the message authentication code, as we're going to see in the following video. ASM receives this PCB and sends it on to ASJ. And so in this case, M again adds its own name M, the hop field encoding the fact that the PCB was received across interface identifier 2 and exiting across the link that is associated with interface identifier 1. Again, M also adds an expiration time and a message authentication code. When J receives this PCB, it encodes the fact that it has received this PCB across the link associated with interface identifier 5, and it also adds the hop field with its own expiration, a message authentication code. Finally, it adds its own digital signature to enable anyone to verify the integrity of this PCB. PCBs are also being flooded, and in this case, we can see several PCBs that are being initiated by AST. And we can see they are flooded throughout the network to find multiple paths from each core AS to AST in this example here. And so we can see there are a multitude of different paths that are being identified. Actually, shown in this slide is only a subset. Additional paths are being identified, for instance, TM, JB is another path that would be created. So let's take a look at path lookup in a bit more detail. So a client requests a path segment to a given isolation domain and autonomous system from the local path server. And so if the down path segments are not locally cached, the local path server then sends a request to a core path server. And finally, given the answer, the local path server replies with up path segments to the local ISD core. And we can see these up path segments here, these yellow and orange segments. For instance, if a client in ASR made this request, and if the request was for a destination in ASS, these additional path segments, and in this case they are down path segments, are being returned to the client. Now, as you can see, some up path segments end at different core ASs than some down path segments. So in order to enable communication end-to-end, we also need additional core path segments, which are shown here in blue, that will also be returned. And now the host in ASR has a lot of different ways to combine its path segments, its up path segments with the core path segments and the down path segments to form end-to-end paths, as we're going to see in the video on the data plane. If a host intends to communicate with a remote ISD, the lookup can be a bit more complex. So the host again contacts its local path server, requesting a path segment to a remote ISD and the remote AS. So in this example, we have a client in ASS that intends to communicate with a client in ASE prime within the green ISD. And so if the downpath segments of ASE prime are not locally cached, then the local path server will contact a core path server. We can see this in this example here. So the orange path server inside ASS contacts a core path server in core ASM. And you see this through this yellow line. If the core path server does not have information about E prime locally cached, it contacts a core path server within the green ISD, in this example, within ASZ, which is part of the green ISD. So in the end, this information is then being relayed to the host. So essentially the host will receive a set of up path segments and a set of core segments, as well as a set of down path segments to E prime. And again, as before, the client has a multitude of choices how to combine these different path segments into end-to-end paths. Now, an interesting question is, how do we actually secure PCB dissemination? SCION is a secure internet architecture, so obviously we need to have ways to protect the whole PCB dissemination process. And first, let's discuss some assumptions. So first, we assume that each AS has a certificate that identifies its AS identifier, which we just denote with AS here, local public key of this AS, as well as an expiration time. And this is signed by one of the core ASs of the ISD. Later, we have a talk on the SCION public key infrastructure and also another talk on the control plane PKI, where you can get more details how this exactly works. But for now, we assume each AS has this certificate, and also there are ways to disseminate these certificates within the network. We also assume that beacon servers know these relevant AS certificates that are needed to verify each PCB. So essentially, each PCB now is signed by the core AS that initiates it, and subsequently each AS that adds its own information to the PCB also signs the updated PCB. This is not unlike the SBGP protocol at this point, which also signs BGP updates that are sent through the network. Also note that the actual data plane information that will be needed, which we call hop fields, are separately protected with message authentication codes that are very efficient to verify, which we're going to see in the video on the data plane. So next we'll look at how SCION can detect failed interfaces. And so in essence, border routers send periodic keep alive messages to the neighboring border routers. And you can see such a keep alive message here, the blue diamond that is sent up. And the border router that receives such a keep alive message resends it and disseminates to all internal beacon server instances that are alive. Similarly, the upper border router sends its own keep alive message that now the lower SCION border router resends to its own beacon server. And in essence, the way we detect failed links is that beacon messages have a threshold number of keep alive messages that they can miss before they declare a link to be inactive. When a link becomes inactive, we have also secure path revocation system in place. And during beaconing, each AS also adds a revocation token to the PCB. And these revocation tokens enable a very efficient authentication of link revocation messages. We're not going to describe this in detail, however, you can look at section 7.3 in the book to then see exactly how this process works. But in essence, when a packet reaches a border router that cannot forward the packet because of a link failure, the router sends back a link revocation message to the originating host. And a router can always do that by turning around the path that is encoded in the packet, as we're going to see in the data plane video. A host that receives one of these link revocation messages then redistributes this revocation message to the local path and beacon servers, and they in turn send it to the core path server to remove any path segments that contain the broken links. So as soon as a link breaks in a very efficient manner, the links are going to be removed and the associated paths that use these links are going to be removed within all the infrastructure. SCION also supports a service Anycast infrastructure to support service-based communication. In service Anycast, a service address type is being used as a packet's destination address, and such a service Anycast message will traverse an up path segment that the source can include, and then each AS on the path up to the core can inspect this service Anycast message. So here we see an example where ASR sends such a service Anycast message through this yellow path through AS's Q, N, and K. And we now see the orange dot in AS's Q, N, and K that represent the given service within each AS. So essentially, the border routers in each AS can inspect the service Anycast message and can determine if the packet should be sent to a local service, and if so, if a local service actually exists, and if not, the packet simply is sent on upwards towards the core AS. So in conclusion, for service Anycast, we have quite a flexible infrastructure to support a variety of service-based communications. SCION has also several mechanisms for failure resilience and service discovery. And we use a consistency service within each autonomous system that offers the following properties. So our consistency service needs to provide leader election, a group membership list, and a consistent database that is distributed across the AS. Currently, we are using Apache Zookeeper for this purpose, but we continue to evaluate other systems that may be more scalable than Zookeeper. So we also have a discovery service that provides a list of active server instances within the AS. And it delivers a combination of information from the consistency service itself, as well as static configurations, in order to provide a highly resilient and reliable information to clients. Next, we're going to look at failure resilience for the specific cases of beacon servers and path servers. So first, let's look at the case of failure resilience for beacon servers. So all the beacon server instances within an autonomous system connect to the consistency service and appear as group members. And there's within each AS a leader election algorithm that determines a master beacon server. PCBs are disseminated with a SCION service address as the destination address, as we've seen on the previous slide. And when a SCION border router obtains one of these PCBs, it selects one running beacon server to deliver the PCB to. This receiving beacon server instance redistributes this PCB to all other instances via our consistency service and specifically via the distributed database. The master beacon server then further analyzes the PCBs received and registers up path segments at the local path server, as we've seen on an earlier slide, selects also down path segments and registers them at core path servers, and also performs the beaconing itself by disseminating PCBs to the neighboring autonomous systems. For the path service, the failure resilience is implemented differently whether the path service is at a core AS or at a local non-core AS. So essentially in a core AS, we rely on the consistency service to perform a leader election algorithm to determine a single master path server for each core AS. There is no leader election happening in a non-core AS. Path replication within a core AS happens by having different path servers send down path segments that are being registered to the master path server and also fetching down path segments from the master path server. And this is to achieve higher performance in order not to be limited by the consistency service. Within a non-core AS, the non-core path servers can use the consistency service for path segment replication, as there are less scalability requirements at that level. SCION also implements the SCION control message protocol. This is similar to the ICMP or Internet Control Message Protocol in today's Internet. And SCMP is similar in the sense that it also provides network diagnostics. So we have SCION equivalents of ping or trace route, as well as error messages to signal problems with packet processing or inform end-hosts about network layer problems. What's different though in the SCMP protocol than in ICMP is that SCMP is a secure protocol. So we have authenticated SCMP messages. We have two different authentication mechanisms, either through a digital signature, and so use then AS certificates to verify the SCMP messages, or also through a mechanism that we call dynamically recreatable keys, or DR key, which we're going to describe in a subsequent video. And in this case of DR key, we can very efficiently create message authentication codes that can authenticate these SCMP messages for individual hosts that then can verify them, and through a very efficient process that we'll explain later. Now that you understand the control plane operations in more detail, I invite you to follow us to explore how the data plane works. What is surprising about the SCION data plane is that it can be even more efficient than today's internet data plane, even though every router has to perform cryptographic operations per packet. We will cover this and other exciting facts in our next video. For more information, please visit our website. Chapter 7 of our SCION book discusses the material we've seen in this video in more detail. You can purchase the book from Springer Verlag, or you can download the PDF from our website. Thank you for watching.